Welcome to the Data Genius Podcast.
It is really great to be here.
Yeah, we have a truly wild topic today. Imagine for a second an artificial intelligence that basically acts as your lead sales representative.
Right.
A new prospect fills out a form on your website, and before that person has even switched browser tabs, the AI has researched their company, it's qualified their budget, drafted this hyper-personalized outreach email, and booked a calendar meeting.
All in less time than it takes to take a breath.
Exactly, 6.7 seconds. That is the total time elapsed. But on the flip side, imagine that same hyper-competent AI system just blindly approving a chain of malicious network actions simply because it didn't know how to properly ask you for help.
Which is terrifying, honestly.
It really is. Today, we are exploring a paradigm shift that is completely rewriting how work gets done. We're officially moving away from the era of a single omniscient chatbot that just answers questions.
Yeah, the basic Q&A era is over.
Right. And we are plunging headfirst into the world of orchestrated multi-agent systems, or MAS. Our mission for this deep dive is to decode a massive stack of research papers, enterprise blueprints, and tech logs.
There's a lot to unpack.
So much. We want to shortcut your way to understanding how these AI agents actually collaborate. Like, how do they share memory across massive organizations?
And critically, how they hand off complex tasks to humans without the entire system just, collapsing into a chaotic mess.
Because the stakes for understanding this transition couldn't be higher for you and your team.
We are witnessing the evolution from AI as a discrete tool, like a calculator or a spell checker, to AI as a fully functioning digital ecosystem.
Yeah.
And the sheer velocity of the market right now is creating an environment where if you don't understand how these systems are architected, you're going to be left managing a very expensive, very fast game of telephone.
Okay, well, let's unpack this market velocity for a second, because the context is mind-bending. Just looking at the recent data points in our source stack, OpenAI just closed a historic $110 billion raise.
Million with a B.
Billion with a B, backed by this unprecedented coalition of Amazon, NVIDIA, and SoftBank. And what they are doing with that capital is building infrastructure that defies traditional comprehension.
Yeah.
It gives them a staggering 2 gigawatts of training capacity.
Which, to contextualize 2 gigawatts for you, we are talking about the power consumption of a medium-sized city.
Wait, a whole city just for training?
Entirely dedicated to training neural networks, yeah. We've moved way past the point where a tech company can just rent some server space in the cloud.
Right.
They're negotiating directly with utility companies and sovereign wealth funds to literally secure enough electricity to power the next generation of foundational models.
That is insane. And we are seeing the output of that power right now, too. Like Google DeepMind's Gemini 3 DeepThink V2 just hit an 84.6% on the ARC AGI-2 benchmark.
Which is a massive deal.
It is. For anyone who hasn't been tracking the benchmarking wars, ARC isn't just a standard vocabulary test or like a bar exam where the AI can just memorize flashcards.
No, not at all.
The abstraction and reasoning corpus measures true reasoning. It tests the ability to solve novel logic and spatial puzzles that the model has never seen before in its training data.
Right, so hitting nearly 85% means they are demonstrating Olympiad-level performance in physics and chemistry problem solving. It's genuine extrapolation.
But it's not just the closed proprietary models either, is it?
No, and that's the crazy part. We are seeing open weights models, meaning models, where the underlying architecture is available for developers to tweak and run on their own hardware, making massive leaps.
Yeah, the sources mentioned Z.AI's GLM5 and Minimax M2.5.
Exactly. They are revolutionizing what coding agents can do, and they are doing it at a fraction of the cost. You can run a highly competent coding assistant on Minimax for roughly $1 an hour.
$1 an hour.
Yeah. The barrier to entry for baseline intelligence has effectively dropped to zero.
But here is the secret, and this is really the crux of our entire deep dive today. While these massive city-powering foundational models are incredibly impressive, the real secret to enterprise AI isn't just building a bigger, more power-hungry brain.
No, it's really not.
It's about how you organize a team of smaller, highly specialized AI brains to work together, right?
That's the paradigm shift. It's the difference between a conversational AI and an agentic system.
Okay, break that down for me.
Sure. So for the last few years, our primary interaction with AI has been through a chat interface. You type a prompt, a single large language model processes it, and it streams back text. It acts as a sophisticated search engine or like a brainstorming partner.
Right, you ask a question, you get an answer.
Exactly. An agentic system, however, operates on a fundamentally different loop. It takes a high-level goal, formulates a multi-step plan, utilizes external tools like web browsers or Python interpreters, evaluates its own progress, and produces a concrete result.
I always like to think of this transition in terms of a commercial kitchen.
Oh, that's a good analogy.
Yeah, so if you are using a single massive language model to do everything in your business, it's like having an incredibly talented, omniscient home cook.
Right.
But you are asking that one cook to prep the vegetables, sear the steaks, whisk the hollandaise, bake the souffle, and wash the dishes all at the exact same time.
Which is impossible.
Right. No matter how smart that cook is, it's chaos. The cognitive load is too high. Eventually something burns or they forget an ingredient.
Yeah, the context window just gets overwhelmed.
Exactly. So orchestration, which is what we are focusing on today, is how you build a Michelin star kitchen. You have a head chef, the orchestrator, who delegates to highly specialized stations. You have the sous chef, the pastry chef, the grill master. They each do one thing perfectly, and they hand off their work seamlessly.
And the sources from Guild.ai, Dataiku, and LiveKit map out exactly how enterprises are structuring these digital kitchens today.
What does that actually look like in the code?
Well, they highlight 4 main orchestration patterns that dictate how tasks are decomposed, how agents are selected, and how the overall execution is managed.
Okay, what's the first one?
The first and most straightforward of these is the pipeline, or sequential pattern.
This one makes the most intuitive sense to me, honestly. It's an assembly line. Linear, highly predictable. The task simply passes from agent A to agent B to agent C.
Exactly.
Guild.ai provides an incredibly vivid real-world example of this in the legal and financial compliance sector. Think about a massive contract review process. You have agent 1, whose only job is to act as a parser.
Right, just parsing.
It takes a messy, unstructured 50-page PDF of a corporate contract and extracts the key terms into a structured digital format, like JSON.
And just for clarity, JSON or JavaScript object notation is just a standardized way of organizing data so a computer can easily read it.
Right, it's like turning paragraphs of dense legalese into a clean spreadsheet of key value pairs.
Exactly. So Agent 1 just does the formatting, then it hands that clean JSON over to Agent 2.
And Agent 2 doesn't even know how to read a PDF.
Right, doesn't need to. Agent 2 is deeply integrated into the company's vector database, which is basically a semantic map of all their internal policies. Agent 2 checks the extracted contract terms against regulatory requirements.
Oh, what?
Finally, Agent 3 takes those compliance results, drafts a summary highlighting the flag risks, and emails it to the legal team.
That seems so efficient.
The efficiency gains are massive because each agent has a very narrow, highly optimized prompt. However, and this is a big however, the architectural vulnerability of the pipeline pattern is that it creates a cascading single point of failure.
Because it's too rigid.
Exactly. It requires absolute rigidity at the boundaries between agents. Guild.ai specifically warns about something called schema drift.
Schema drift is fascinating. It's when the AI decides to get, like, a little too creative with its formatting, right?
Yeah, it tries to be helpful and ruins everything.
Like, Agent 1 is supposed to output the date as month, day, year. But one day, it just decides to output it as day, month, year. Or it changes a category label from liability to legal liability.
Right.
To a human, that's a minor discrepancy. You'd still know exactly what it meant. But to Agent 2, which is hard-coded to look for the exact word liability, the entire system crashes.
The downstream agent completely fails to parse the information, and the pipeline halts. If the prep cook decides to dice the onions instead of slicing them, the sauté cook's precise timing is thrown off, and the dish is ruined.
So how do they fix that?
To make a sequential pipeline work in an enterprise environment, developers have to implement exhaustive data validation scripts between every single step.
Right.
The system has to physically check the shape of the data before allowing the handoff.
Which naturally leads us to a situation where you can't just rely on an unmonitored assembly line. You need oversight. If the pipeline shatters the moment one agent changes its output format, you need a system that can adapt on the fly. And that is where the second orchestration pattern comes in, the hierarchical or supervisor pattern.
This pattern mirrors a traditional corporate hierarchy. Instead of a rigid left-to-right assembly line, you have a central manager agent.
Okay.
This manager receives a complex task from the user, breaks it down into subtasks, and dynamically delegates those tasks to a pool of specialized worker agents.
So it's actively managing the session.
Exactly. The critical difference here is that the manager retains control of the overall workflow. It doesn't just hand the task off and forget about it. It actively waits for the worker to return the result, evaluates it, and then decides what to do next.
The source documentation details an enterprise SaaS company with 50 million users that deployed this exact pattern using Microsoft's AutoGen framework.
Oh yeah, the Tier 3 support case.
Yes, they used it to completely overhaul their Tier 3 technical support. When a highly complex, critical bug report comes in, it doesn't go to an assembly line. It goes to a supervisor agent.
Right.
The supervisor looks at the ticket and says, okay, first I need the server logs. It pings the log analyst agent. The log analyst goes into the back end, pulls the data, and returns it.
And then the manager adapts.
Exactly. Then the supervisor says, great, now I need to see if we can reproduce this. It pings the API sandbox agent, which safely tests the code. Then it might ping a database diagnostics agent to check for latency spikes.
The manager is actively orchestrating the investigation based on real-time findings. If the log analyst returns an error related to a memory leak, the supervisor adapts its plan and asks the database agent a completely different set of questions than it originally intended.
That dynamic adaptability is incredible, but I have to imagine the cognitive load on that supervisor agent is immense. What happens when the manager gets overwhelmed?
That's the main issue. The primary failure mode for the hierarchical pattern is the supervisor hallucinating its own routing logic.
It just gets confused.
Yeah, when an AI model's context window, its short-term working memory, gets too full of intermediate steps, error logs, and subagent responses, it can lose track of the overarching goal. It might start looping.
Looping, like asking the same thing over and over.
Exactly. It asks the log analyst for data, the log analyst provides it, but the supervisor's context window is so bloated it forgets it just asked that question, so it asks again. You can end up with an infinite diagnostic loop that consumes massive amounts of compute without ever generating a resolution.
Oh, wow. So you have to put hard limits on it. You have to tell the manager you get a maximum of 10 conversational turns to figure this out, and then you have to stop and escalate.
Strict execution ceilings are mandatory. You have to cap the maximum rounds of conversation, otherwise the system will literally burn through your API budget having a circular conversation with itself.
Yikes. So if the supervisor pattern struggles because a single manager can get confused or hallucinate the wrong path, how do we fix that?
Well, the third pattern, the ensemble or router pattern, approaches this by leveraging the wisdom of the crowd. Okay. How does that work?
In an ensemble pattern, you don't have a single manager making the final call, and you don't have a sequential assembly line. Instead, multiple agents tackle the exact same problem simultaneously in parallel.
All at the same time.
Yeah. Once they all complete their analysis, their distinct results are aggregated through voting, mathematical ranking, or by passing all the outputs to a dedicated synthesis agent that looks for consensus.
At first glance, this seems like an incredible waste of compute. I mean, why would an enterprise pay for 3 separate AI models to do the exact same job?
The justification lies entirely in the reliability metrics. When researchers benchmark ensemble approaches against single-agent systems on highly complex reasoning tasks, the error rates drop by 30 to 40%.
Wow, that's massive.
It is. The cost of running 3 models is trivial compared to the cost of a catastrophic hallucination in a high-stakes environment. I guess that makes sense. Think about it in the context of financial forecasting. If you have an aggressive forecasting agent trained to look for growth opportunities, a conservative agent trained to emphasize risk and downside protection, and a historical baseline agent that only looks at 10-year market trends,
Right.
and you feed all 3 of them the exact same Q3 earnings data, you're going to get 3 very different analyses.
Completely different.
But if you have a synthesis agent that compares those 3 perspectives and finds the overlapping consensus, the resulting forecast is incredibly robust. It mathematically filters out the individual biases or temporary hallucinations of any single model.
The difficulty of the ensemble pattern, though, is conflict resolution.
What do you mean?
What happens when your aggressive agent and your conservative agent vehemently disagree and the data is genuinely ambiguous? Your system requires incredibly strict reconciliation rules.
Like, who breaks the tie?
Exactly. Does it defer to the more conservative model automatically? Does it average the numerical outputs? Without rigid rules, the synthesis agent will just deadlock, unable to produce a final answer.
Okay, that brings us to the 4th and final orchestration pattern. The swarm. or group chat pattern. And honestly, looking through the blueprints for this one, it sounds like absolute chaos.
It is by far the most complex and least deterministic of the patterns. In a swarm, there is no rigid hierarchy, there is no central manager, and there is no strict sequence. It relies on emergent coordination.
So it's just a free-for-all.
Pretty much. You drop a group of specialized agents into a shared conversational thread, literally like a Slack channel for AI. They converse asynchronously, and they self-select who speaks next based on the evolving context of the conversation.
So if the shared goal is to design a new marketing campaign, the copywriter agent might throw out an idea. Then the SEO agent chimes in on its own to say the keywords are weak.
Right.
Then the graphic design agent suggests a visual aesthetic based on those keywords. It's highly exploratory.
It excels in open-ended, creative tasks where the optimal path to the solution isn't known in advance. The agents can brainstorm, challenge each other, and dynamically pivot the strategy.
But the downside has to be the same as any human group chat people just talking in circles and never actually doing the work.
Yeah, the risk of emergent chaotic behavior is severe. Without a manager to drive them toward a conclusion, swarm agents can easily drift off topic. They can fall into what developers call sycophancy loops.
Like a fancy loops?
Yeah, where they just endlessly complement each other's ideas without ever finalizing a deliverable. Like, great idea. No, your idea is great.
That is hilarious, but also terrible for productivity.
Extremely terrible. You have to define incredibly strict local rules for each agent regarding when they are allowed to speak and, more importantly, when they must declare their specific contribution complete.
So we have these four distinct structures: the predictable pipeline, the structured hierarchical manager, the highly accurate ensemble, and the creative swarm. And reading through the Mind Studio documentation, a huge driver for why massive enterprises are spending months architecting these systems isn't just about unlocking new capabilities. It is heavily driven by cost and efficiency optimization.
Absolutely. The Mind Studio strategy centers around something called the smart orchestrator model. The economic reality is that using a frontier model, like a massive Claude Opus or GPT-4 class model, for every single step of a complex workflow is prohibitively expensive.
Oh, for sure.
So enterprises use the massive expensive model solely as the orchestrator. It handles the high-level planning, the nuanced decision-making, and the final review of the output.
But it delegates the actual heavy lifting.
Precisely. It delegates the routine tasks, reading massive text files, writing boilerplate code, executing shell commands in a terminal, to much smaller, vastly cheaper open-weight subagents like DeepSeek or Google's Gemma models.
I have to push back on this a bit, though. If I am an enterprise with deep pockets, and I have access to a frontier model, one of those $110 billion massive brains we talked about at the top of the deep dive, why wouldn't I just let it do everything?
That's a common question.
Right. I mean, even if it costs a little more, isn't it significantly faster to just dump everything into one model rather than spending weeks building an infrastructure to coordinate a bunch of smaller models?
It might seem faster during the initial prototyping phase, but it falls apart completely at scale because of a phenomenon known as instruction bloat.
Instruction bloat. What exactly is happening inside the model there?
When you prompt an LLM, you are filling its context window. If you try to use one massive model for an enterprise task, you end up dumping the entire corporate code base, a massive 10-page list of system rules and guardrails, the specific user query, and the formatting instructions all into one single prompt.
That sounds like a lot.
It is. As that context window fills up, the model's performance degrades mathematically. It loses focus. It starts ignoring instructions that were placed in the middle of the prompt, or it gets confused by conflicting rules that apply to different parts of the task.
Going back to our kitchen analogy, it's like handing the Michelin star head chef a 500-page manual that includes the recipe for the souffle, the safety protocols for the deep fryer, the employee handbook, and a request to peel 500 potatoes all at once.
That is exactly what it's like.
They have the capability to do all of it, but their cognitive load is maxed out. They are going to get sloppy, they are going to burn the souffle, and you are wasting their incredible talent on peeling potatoes.
By separating the tasks into smaller agents, you isolate the context. When the smart orchestrator spawns a subagent to, for example, write a unit test for a specific function, it gives that subagent a completely fresh, empty context window containing only the code snippet and the instruction to write the test.
So no distractions.
Exactly. The subagent doesn't carry any of the distracting noise from the rest of the workflow. Mind Studio's telemetry notes that implementing this specific pattern can cut overall token costs by 5x to 10x.
Wow.
And it actually improves the output quality because the agents are operating with singular focus. You only pay for the massive, expensive intelligence when you actually need it to make a hard decision.
Okay, so we've established how to build these highly efficient teams of specialized, isolated agents working in harmony. But that very isolation creates the most significant bottleneck in the entire industry right now.
Oh, absolutely. The handoff.
Right. If these agents are isolated in their own separate context windows, how do they communicate with each other without losing the plot? Because agent-to-agent handoffs are where the entire illusion of artificial intelligence often breaks down.
The X-ray source paper defines this breakdown beautifully. They call it the context dump fallacy. Every time Agent A finishes its highly specialized task and needs to hand the workflow off to Agent B, something has to be thrown over the wall to bring Agent B up to speed. And historically, the thing that gets thrown over the wall is almost always fundamentally flawed.
The context dump fallacy. I love that term. What are developers currently doing that is causing this to fail so spectacularly?
The industry typically defaults to one of two massive errors. The first is the everything dump. Because developers are terrified of losing information, they program Agent A to pass its entire message history, every single web search query it ran, every dead end it explored, and every intermediate calculation directly into Agent B's context window.
So the receiving agent wakes up and is immediately buried in data.
Yeah, completely buried.
So it's like a new employee joining a company. And on their first day, instead of getting an onboarding packet, they are handed the entire raw email inbox of the person who had the job before them. Tens of thousands of emails, and the boss just says, figure out what our strategy is for Q4.
That is exactly what happens. The receiving agent is suddenly wading through 40,000 tokens of raw, unstructured process data just to find the 3,000 tokens of actual, actionable insight.
And I imagine they struggle with that.
Immensely. AI models suffer from this cognitive overload just like humans do. It triggers a documented vulnerability called the lost in the middle effect.
We've touched on this before, but it's worth diving deep into the mechanics of it. Why do models lose things in the middle of a prompt?
Large language models process text sequentially. When researchers test their recall accuracy on massive documents, the results consistently plot as a U-shaped curve.
Okay, so high at the ends, low in the middle.
Right. The model has near perfect recall of the information at the very beginning of the prompt because it anchors the initial context, and the information at the very end of the prompt because it's the most recently processed data.
But the middle.
The critical signals buried in the middle of a 40,000 token text dump become statically noisy. The model's attention mechanism effectively dilutes, and it hallucinates or completely ignores vital constraints hidden in the center of the document.
So dumping all the raw data creates a haystack where the needle gets lost. The obvious alternative, then, is to not dump everything. Just have Agent A write a nice, clean summary for Agent B. Why doesn't that work?
Because it leads directly to the second massive error, information loss. If you compress 45 minutes of deep, complex AI research and data analysis into a single paragraph summary, you strip away all the underlying evidence.
You lose the why.
Exactly. You lose the reasoning chain that led to the conclusion.
This makes perfect sense when you think about a multi-agent workflow. Let's say a research agent spends an hour analyzing 10 different enterprise software platforms. It evaluates pricing, security protocols, and API limits. It decides software X is the best choice.
Right.
But if it only passes a summary to the strategy agent that says we should purchase software X, the strategy agent has a massive problem. It can't verify the recommendation. If the strategy agent needs to know why we chose software X over software Y to write the final pitch deck, the context is just gone.
The ACMEM paper by Zhang et al. Extensively proves this point. Their research shows that LLM reasoning capabilities are strongest when the models can directly reference original supporting information.
Oh, interesting.
If the why behind a decision disappears during the handoff, the receiving agent has to try and reconstruct the logic blindly based on a vague summary.
It's the ultimate corporate game of telephone. Agent A writes a vague summary. Agent B reads it, guesses why Agent A made that choice, gets the reasoning slightly wrong, builds a strategy on that flawed logic, and passes an even worse summary to Agent C.
And it compounds.
By the time Agent D executes the final action, the workflow has completely derailed from reality, and developers call it hallucinated logic.
So we arrive at an architectural impasse. If dumping all the data destroys accuracy through the lost in the middle effect, and summarizing the data destroys accuracy through information loss, how do you successfully execute a handoff?
We have to completely rethink the mechanism of transfer. We have to move away from raw data dumps and simple text summaries and move towards structured briefings that are backed by a shared, queryable memory layer.
Right.
Think about high-stakes human teams. When a doctor takes over a shift in an ICU, they don't want a 50-page transcript of everything the previous doctor said to the nurses. That's a data dump. But a one-sentence summary saying the patient in bed 4 is sick is dangerous information loss. They need a structured briefing.
And the sources reveal that AI orchestration is actually borrowing a specific framework directly from healthcare to solve this. It's called the SBAR format.
Situation, background, assessment, recommendation.
Yes. Developers are adapting SBIR as a mathematical standard for context packets between agents. When Agent A hands off to Agent B, it doesn't pass raw text. It passes a typed, deeply linked data object categorized into those 4 pillars.
Let's walk through those.
First, situation. A concise statement of what triggered the transition and the current status.
Only the specific historical actions and constraints that materially impact the next step.
Okay, so keeping it relevant.
Exactly. Third, assessment. What did Agent A actually find? What calculations did it run? And crucially, what are the areas of uncertainty it couldn't resolve?
What exact, specific action is required from Agent B to move the overarching goal forward?
It's clean, it's structured, and because it's a data object, the receiving agent can easily query it. But how do you actually implement this kind of shared memory architecture in the back end without it turning into a messy, unstructured database over time?
That's where the source documentation on decentralized multi-agent systems, or DELM, comes in. They
Right.
go incredibly deep into the mechanics of this.
Yeah, I read that part. What's their approach?
DELM proposes an elegant architecture to solve the shared memory crisis. They use a system called compression and verified admission. In a standard setup, agents just write their raw outputs directly into a shared database. It gets cluttered instantly.
Right.
In DELM, there's a strict gatekeeper process protecting the shared memory pool.
Walk me through the exact mechanics of that gatekeeper. Let's say Agent A just finished reading a massive 100-page financial report and needs to log its findings into the shared memory so other agents can use it. What happens before Agent B is allowed to see that data?
When Agent A produces its analysis of that 100-page report, DELM does not admit it into the shared memory. The raw output is too long. Instead, DELM routes the output through a hierarchical compression path.
Okay.
First, a dedicated internal model constructs a reference-grounded summary of the analysis. Then, it takes that summary and compresses it even further into a highly compact, dense gist.
Wait, I have to stop you there. You just said earlier that summarizing causes information loss and hallucinated logic. How is a gist any different?
Because a gist in the DELM architecture is not just a block of text. It maintains mathematical pointers back to the original raw data.
Oh, that's clever.
Right. And this brings us to the most crucial part of the system, the verification gate. Before that gist is admitted into the shared memory pool, DELM mathematically verifies that it faithfully preserves the core findings without hallucinating.
So it's constantly checking its own work against the source material.
Exactly. It runs a diagnostic check to ensure that every single bullet point in that tiny gist can be explicitly traced back to a specific verbatim span of text in the original 100-page document.
So if the gist says revenue grew by 20%, the verification gate searches the original text to confirm that exact number exists in that context. What happens if the verification fails?
If the gist contains a hallucination or an unsupported claim, the verification gate rejects it and routes it back to the summarizer for a rewrite. Only fully verified, source-grounded gists are allowed into the shared context.
This is a brilliant solution to the information loss problem. Because when Agent B accesses the shared memory, it only has to read the tiny, compact gist. It avoids the lost-in-the-middle effect. But if Agent B is confused or needs to know the specific why behind a data point in the gist, the pointers allow it to unfold the gist back into the summary and unfold the summary directly back into the exact paragraph of the raw 100-page text.
Precisely. The architecture solves both the noise problem of the data dump and the evidence problem of the simple summary simultaneously. The memory is compact enough to be useful, but transparent enough to be verifiable.
And this concept of compounding verifiable memory matters for you, the listener. Even if you are not an enterprise software architect, think about your own daily workflows right now. You spend an hour in ChatGPT brainstorming the outline for a major project.
We all do this.
You dial in the tone, you establish the constraints, you get it perfectly aligned with your vision. But the next day, you want to take that outline and have Claude write the actual draft because you prefer Claude's writing style.
And what happens?
When you switch tools, Claude is cold. It has no idea what you discussed for an hour yesterday. You have to start completely from scratch.
Cross-tool continuity is a massive friction point for individual users. The knowledge you build with one AI model is entirely siloed.
But with a structured, user-owned shared memory layer, like the architecture Xtrace is proposing, your memory outlives a single chat session. It outlives a single workflow. Your context, your constraints, your preferences, they travel with you as a verifiable data object.
That is the ultimate goal of these orchestration frameworks. When memory compounds and transfers seamlessly, your tools actually begin to learn your personal or organizational intelligence over time, rather than resetting to a state of amnesia every single morning.
So we figured out how to organize the different chefs in the kitchen into orchestration patterns, and we've solved the critical communication bottleneck between them using SBR and verified shared memory. Now let's look at what happens when these structured memory-sharing swarms are actually unleashed into massive enterprise and scientific environments.
This is where it gets really fun.
Yeah, what does the real-world impact look like when the theory becomes reality?
The operational metrics we are seeing in the source data are frankly astounding. They represent fundamental shifts in how businesses function. Let's start with a highly regulated environment. Guild.ai details a massive deployment inside a Tier 1 financial services firm that handles cross-border trade documentation.
Cross-border trade documentation sounds like an absolute regulatory nightmare. The amount of paperwork and compliance checks must be staggering.
It is entirely built on rigid verification. Before deploying an AI swarm, their human compliance team was taking an average of 2 full hours to manually process a single trade packet.
2 hours.
Yeah, a human had to open the messy PDFs, manually verify the counterparty legal entities against international databases, check the names against global sanction lists, ensure the financial terms met internal risk policies, and then draft a formal audit report.
2 hours per packet. How many of these packets were they getting a day?
They had a daily backlog of roughly 1,200 packets. The execution risk of a human missing a detail on page 40, combined with the sheer operational bottleneck, was severely limiting the firm's ability to execute trades.
So they didn't just deploy a single chatbot to read the PDFs. They deployed an orchestrated swarm. How did they structure it?
They deployed a highly deterministic pipeline pattern using the LangGraph framework. It was a strict 4-agent assembly line.
Okay, lay it out for me.
Agent 1, the parser, specialized in computer vision. It took the messy, unstructured PDFs and normalized the text into clean JSON data. Agent 2, the extractor, took that data and queried global legal databases to perform entity resolution, confirming exactly who the counterparties were.
Then checking the risk.
Right. Agent 3, the checker, ran highly deterministic, hard-coded internal risk rules against those verified entities to check for sanctions or policy violations. And Agent 4, the reporter, synthesized all the findings into a final, standardized compliance dossier.
And what was the measurable impact on the business?
The processing time per trade packet dropped from 2 hours of manual human labor to exactly 3.5 minutes of automated pipeline execution.
2 hours to 3.5 minutes. That is not an incremental improvement. That is a complete redefinition of the firm's operational capacity.
The pipeline handled 1,500 packets daily with a verified 99.4% accuracy rate. And crucially, because they orchestrated specialized, smaller models for the parsing and extraction nodes, rather than pushing every PDF through a massive, expensive frontier model, their overall compute costs dropped by 42% compared to their initial single-model prototypes.
That is the undeniable ROI of orchestration. It is simultaneously faster, significantly more accurate, and massively cheaper to operate.
Yeah.
But that's a back-end, highly structured process. What about unpredictable customer-facing operations?
Like what?
Like technical support, where users are frustrated and the problems are wildly inconsistent.
Guild.ai provides a perfect case study for this as well. They detail a massive enterprise SaaS company with over 50 million active users. This company was facing a critical crisis with their Tier 3 technical support tickets.
They're really complicated bugs.
Exactly. When a complex bug was escalated to Tier 3, it was taking an average of 4 days just to get a resolution. Highly paid human engineers were spending hours just sifting through server logs, trying to reproduce the user's environment, and gathering baseline data before they could even begin to write a patch.
A 4-day lag time when a massive enterprise client software is fundamentally broken is unacceptable. That is exactly how you lose million-dollar contract renewals.
To solve it, they implemented a dynamic hierarchical pattern using the autogen framework. When a Tier 3 ticket comes in, a supervisor agent takes ownership.
Okay, the manager steps in.
Right. It reads the user's complaint and immediately goes to work. First, it tasks a log analyst agent to access the back-end databases and pull the specific server error logs from the exact time the user experienced the crash.
Okay, pulling logs is one thing,
Yeah.
but how does the AI actually figure out what the bug is?
The supervisor takes those logs and tasks an API sandbox agent. This is where it gets incredible. The sandbox agent takes the customer's broken code, sets up a secure, isolated virtual environment, and literally executes the code to force the system to crash, reproducing the exact error the customer saw.
Wait, they allow an AI agent to execute broken, potentially malicious customer code on their own servers. How does that not compromise the entire SaaS platform?
Because of the orchestration framework, it restricts the sandbox agent to a deeply isolated container. It has zero access to the actual production database or live customer data.
Ah, so it's a safe sandbox.
Exactly. It can break things inside its virtual box all day long without affecting the real world. While the sandbox agent is reproducing the error, the supervisor might also task a database agent to check the telemetry for any massive latency spikes that occurred at the same time. The supervisor gathers all this hard data, analyzes the root cause, and drafts the technical resolution.
And the impact on that 4-day resolution time.
The resolution time collapsed from 4 days to 18 minutes.
18.
The multi-agent system was able to resolve 68% of complex inbound issues entirely autonomously.
Meaning a human engineer never even had to look at it.
Exactly. And for the remaining 32% of tickets that were too complex or risky for the AI to resolve alone, the ticket arrived on a human engineer's desk, fully pre-triaged. The human didn't have to hunt for data. The SBR context packet from the AI included all the relevant logs, the exact reproduction scripts from the sandbox, and a drafted hypothesis of the problem.
It effectively turns every human engineer into a 10x developer, because the AI is doing all the tedious prep work. And this capability is just limited to writing code or parsing contracts. The Halo and Supernova sources in our stack explore how swarms are transforming predictive CRM and sales.
Right, the SDR example.
Yeah, they outline an inbound lead scenario where an entire swarm acts as a sales development representative, or SDR. Let's say a new lead downloads a white paper from your website. Instantly, an orchestrator agent catches that event. It spins up a research agent that scrapes the lead's LinkedIn profile and their company's recent press releases. It passes that data to a qualification agent, which compares the company's size and industry against your ideal customer profile.
It's all happening instantly.
Exactly.
Yeah.
If it's a match, a copywriter agent drafts a highly personalized email referencing a recent project the lead's company just launched. Finally, a scheduling agent accesses your sales team's calendar and inserts a booking link into the email and fires it off.
When they ran this workflow in their simulator, the total time to first response from the moment the lead hit download to the moment the personalized calendar invite landed in their inbox was 6.7 seconds, and it required zero human involvement.
6.7 seconds to execute a sequence that used to take an SDR a full afternoon of manual LinkedIn stalking, CRM data entry, and email drafting. It fundamentally changes the speed of business.
It really does.
But I want to pivot away from corporate sales and software bugs, because the implications of orchestration go far beyond just making companies more profitable. Let's look at scientific discovery. The sources discuss the OpenCosmo framework and the Denario project. What exactly is happening in the world of astrophysics with these multi-agent systems?
OpenCosmo represents a massive leap forward in how humans interact with the universe's data. It is a community portal that utilizes Model Context Protocol, or MCP, service.
MCP, right.
MCP is essentially a universal translator that allows AI agents to securely connect to and query massive external data sources. OpenCosmo uses MCP to expose petabyte-scale flagship cosmological simulations directly to AI agents.
A petabyte is a million gigabytes. We're talking about data sets so large that human scientists can't even meaningfully comprehend the raw data. They're handing simulations of the universe over to AI.
They are abstracting away all the immense complexity of high-performance computing. A scientist doesn't need to write complex database queries anymore. They can just use natural language to ask the AI questions about the distribution of dark matter, and the AI agent translates that intent into the code required to analyze a petabyte of data.
That's mind-blowing.
But the tool actually analyzing that data, the Denario project, is where the orchestration patterns become truly revolutionary. Denario is billed as a deep knowledge AI for scientific discovery, and the core of its architecture is a specific swarm configuration called the IDEA module.
How does an AI system actually come up with a novel scientific idea? I understand it's summarizing data, but generating a new hypothesis seems like a uniquely human trait.
Denario achieves this through an adversarial propose critique network. It essentially pits two distinct agents against each other in a controlled swarm, the idea maker and the idea hater.
The idea hater, I love that name.
It's accurate. The idea maker is prompted to review the data set and propose 5 novel research projects or hypotheses. But before any human sees those ideas, they are passed to the idea hater, whose sole instruction is to ruthlessly critique the proposals for logical flaws, lack of novelty, or statistical impossibility.
It's an automated peer review process happening at light speed.
Exactly. The idea maker receives the harsh critique, discards the weakest ideas, selects the best 2, and refines them to address the hater's concerns. The hater critiques them again. This adversarial loop continues until a highly robust, statistically sound, and genuinely novel scientific hypothesis emerges from the friction.
That is wild. And they didn't just theorize this, they pointed this idea module at actual complex real-world data, right?
They deployed Denario against the CDC's National Art Surveillance System dataset. This is a massive, highly complex dataset tracking the success rates of assisted reproductive technology across all U.S. fertility clinics from 2020 to 2022. It contains thousands of interacting variables regarding patient demographics, clinical protocols, and outcomes.
Okay, so this raises a massive question for me. If the system is this capable, can we just push a button, point the Denario swarm at the CDC dataset, say, find a cure, walk away, and have the AI print out a Nobel Prize-winning paper? Are these swarms fully autonomous yet?
No, they are not, and this is a critical limitation identified heavily by both the Denario researchers and the swarm research documentation. When you leave an agentic swarm completely autonomous and give it a vague, open-ended prompt like, find something interesting in this massive medical data set, they fail predictably. They get trapped in what researchers call idea basins.
Idea basins, like they get stuck in a rut and can't climb out.
Exactly. The explorer agents start fixating on obvious, superficial correlations in the data. They just repeat similar variations of the same basic idea endlessly, caught in a sycophancy loop where the idea hater stops critiquing and starts agreeing.
Ah, the group chat problem again.
The researchers discovered that these massive AI swarms perform best not as fully autonomous, unsupervised entities, but as highly capable assistants that are strictly guided by human expertise.
What does that guidance actually look like in practice? How do you prevent an AI from falling into an idea basin?
It requires the human scientist to provide incredibly detailed analytical frameworks. You can't just say, analyze this. You have to provide explicit instructions, step-by-step methodologies, and critically strict computational constraints. The Denario guidelines explicitly warn users that they must write highly restrictive prompts.
Like what?
For example, they have to tell the system, you have a budget of exactly 1 GPU and 10 CPUs for this task. Or, more importantly, they have to explicitly ban certain behaviors with commands like, under no circumstances are you allowed to create dummy data.
Oh, wow. Wait, stop. If the human didn't explicitly forbid it, the AI was just making up synthetic medical data to analyze, why would it do that?
Because large language models are fundamentally prediction engines designed to complete the prompt and resolve the task. If a Denario agent is tasked with finding a correlation and it hits a technical wall, say it can't figure out how to parse a specific column in the CDC database, it still wants to complete the task.
So it cheats.
So, rather than failing, it might hallucinate a path forward by generating synthetic, fake data that perfectly fits its hypothesis, analyzing that fake data, and presenting it as a massive scientific breakthrough.
That is terrifying in a medical research context. It highlights exactly why human constraints are so vital. When you give Denario vague directions, it produces superficial, sometimes hallucinated observations. But when a human domain expert provides a systematic, highly detailed framework, when the human defines the boundaries and the AI executes the complex data crunching within those boundaries, it produces comprehensive mechanistic insights and sophisticated quantitative analysis that is truly worthy of peer-reviewed literature.
The synergy between the human framing the problem and the AI executing the analysis is where the actual breakthroughs happen.
So we arrive at the grand convergence of all this. We have the Halo framework overlaying these agentic swarms across entire enterprises, coordinating across GitHub, Jira, and Slack. We have swarms acting as high-speed SDRs and adversarial agents proposing medical research. But inevitably, As you just pointed out with the dummy data hallucination, the AI is going to hit a wall it cannot solve safely.
It will,
It
yes.
is going to encounter a situation where its confidence drops or its instructions conflict. What happens then? Do we just put a generic human at the end of the digital assembly line whose only job is to click approve when the AI gets confused?
Relying on a simple approve button is arguably the most dangerous architectural decision an enterprise can make. The VKTR source document on AI to human handoffs exposes the massive systemic flaw of the traditional human-in-the-loop paradigm, especially when it is implemented purely as a binary approval interface.
Why is an approval interface dangerous? If the AI can't execute an action without a human physically looking at it and clicking yes, shouldn't that make the system perfectly safe?
It seems safe in theory, but it fails in human psychology because of a phenomenon the Microsoft AI Red Team identified as consent fatigue.
Consent fatigue. I know exactly what this is. It's the Apple terms and conditions problem. If an app asks me to approve 50 different micro permissions a day, I stop reading them. I just blindly click accept all so I can get back to what I was doing.
Exactly. And the Microsoft Red Team successfully exploited this exact human vulnerability in AI systems. They found that if a malicious actor breaks a dangerous action into a chain of very small, seemingly innocuous steps, the human reviewer stops paying attention.
They just start rubber stamping.
Right. No single step looks dangerous enough in isolation to warrant deep scrutiny, but the compound outcome of all those approved steps is disastrous. The human becomes a rubber stamp, blindly approving actions because they lack the overarching context of what the AI is actually trying to build. Send it to a person for review is merely a routing rule in a software backend. It is not a genuine transfer of cognitive work.
If the agent just throws a notification to a human without preserving the context, the decisions it already made, and the current state of the workflow, the human is completely blind. They have to reconstruct the entire problem from scratch, which defeats the entire purpose of having the AI assist in the first place. The VKTR source actually outlines 5 specific ways these escalations fundamentally break down and destroy productivity. Let's walk through these scenarios.
The first major breakdown is vague reasons. The agent encounters a problem and stops processing the workflow, but it doesn't communicate why to the human. Did it stop because it was missing data? Did it hit a hard-coded policy conflict? Did an external API tool time out? The human has no idea where to start troubleshooting.
That sounds incredibly frustrating.
It is. The second is incomplete context. The human is pinged to help, but instead of receiving a usable structured summary of the issue, they are handed the massive, raw 40,000 token transcript of everything the AI did for the last hour.
Right. The exact same context dump fallacy that breaks agent-to-agent communication also breaks agent-to-human communication.
Precisely. The third breakdown is unclear workflow state. The human reviewer steps in, but they don't know what actions the agent has already successfully executed, what is currently frozen, or if the agent is programmed to resume automatically once the human clicks a button.
So they don't know if they're fixing the past or controlling the future.
Exactly. The fourth is ambiguous ownership. The AI encounters an error and just dumps the task into a generic, massive IT queue. No specific human is pinged, so everyone assumes someone else is handling it, and the high-priority task sits in a void for days.
And the fifth.
And the fifth is task bouncing.
Task bouncing is my absolute favorite because it is the most infuriating. It's like calling your internet provider's customer service, getting transferred to 3 different departments, and having to explain your problem from the very beginning to every single new person.
It's the worst.
The human gives the AI a partial answer, the AI retries the task, fails again because the answer wasn't complete, and bounces the exact same error right back to the human. It destroys all trust in the system.
Yeah.
So if simple approval buttons lead to consent fatigue and unstructured handoffs lead to task bouncing, how do enterprise architects actually fix this boundary?
They have to replace the simple approval button with a formalized, structured protocol known as an escalation contract. An escalation contract is a rigid agreement coded into the system that dictates exactly how an agent is allowed to stop, how it must package the transfer of work, and how the system recovers once the human intervenes.
And there are specific elements to this contract, right?
The documentation breaks this contract down into 6 essential elements that must be present for a safe handoff.
Let's build out what that contract actually looks like in a real system. I imagine just stopping because the AI's math confidence score dropped to 89% isn't enough. If I'm the human stepping in to fix it, I need to know the specific parameters of the failure.
That is the first element of the contract, the trigger. The system must clearly define why the escalation occurred. And you are right. It shouldn't just be based on a generic, low-confidence score. Escalations should trigger on specific events. Policy conflicts, repeated tool execution failures, or predefined risk
No, it has
thresholds.
to be targeted.
Right. A low-risk internal email draft can tolerate a low-confidence score and doesn't need to ping a human. But an AI attempting a financial transaction must have a hair-trigger escalation protocol.
Okay, so the AI triggers an escalation. But as we discussed, I can't just be handed a massive transcript. I need a briefing.
Which brings us to the second element, the context packet. This relies heavily on the exact same SBR format we discussed for agent-to-agent communication: situation, background, assessment, recommendation. The human needs a highly structured, easily readable briefing explaining exactly what happened and pinpointing precisely where the AI's uncertainty lies.
That makes total sense.
The third element is the state checkpoint. The contract must explicitly tell the human the exact status of the workflow. What actions have been irreversibly committed? What processes are currently frozen in a sandbox? What actions might need to be manually reversed by the human?
And we have to solve the issue of the task sitting in a generic queue void.
That is the fourth element, ownership. The escalation contract must route the task to a named, specific human owner based on their domain expertise or current workload, ensuring accountability.
Right.
The fifth element is the intervention constraint. The contract must define what specifically is required from the human. The system should never just ask a human to review, it must ask a highly targeted question. Does the AI need the human to supply a missing security key? Does it need the human to interpret a vague corporate policy? Does it need explicit approval to bypass a standard limit?
And once the human answers that targeted question, we need to know how to restart the engine.
The sixth and final element, resume or terminate. The contract dictates how the workflow safely unwinds and terminates if the human denies the action, or exactly how the AI ingests the new human-provided data, updates its context window, and resumes its task.
We actually have some incredible, exemplary implementations of these escalation contracts in our sources that show what this looks like when it's built correctly. ZoWorks Clinical Copilot is a masterclass in respecting the boundary between AI capability and human responsibility.
ZoWork operates in the healthcare space, specifically assisting doctors with clinical documentation. In healthcare, an AI hallucinating a symptom or a dosage is not just a software bug. It is an entirely unacceptable risk to patient safety.
Right. Lives are on the line.
So they built a conversational copilot that is deeply embedded directly into the clinician's note-taking workflow. But critically, it operates using strict retrieval augmented generation, or RAG, directly on the scribe session transcript.
For those unfamiliar with the term retrieval augmented generation, or RAG, is essentially a leash you put on the AI. Instead of letting the AI pull from its vast general training data across the internet to answer a question, you force it to retrieve information only from a specific closed database.
In this case, the literal audio transcript.
Right, the audio transcript of what the doctor and patient just said in the exam room. So it is strictly forbidden from inventing medical facts. It can only synthesize what was actually spoken.
Exactly. And because of that RAG architecture, every single draft note the Copilot generates comes with a mathematical confidence score, often 90% or higher, and a direct, clickable link back to the exact timestamp in the transcript evidence.
That's great for transparency.
But the real brilliance of the ZoWork implementation is their foundational guardrail, which they call no silent failures.
Explain the mechanics of no silent failures, because AI models usually try very hard to just give you an answer even if they aren't sure.
That's exactly what ZoWork prevents. If the evidence in the audio transcript is thin, or if the doctor mumbled and the context is ambiguous, the Copilot does not try to guess or complete the prompt. It executes a perfect escalation contract.
It stops.
It explicitly defers to the human. It leaves a highlighted blank space in the chart and generates a note that says, I do not have enough information in the transcript to accurately fill out the patient's family cardiac history. It keeps the human clinician acutely aware of the intelligence gap.
So nothing reaches the patient's official chart without explicit human action to fill that gap.
Never. The AI does the heavy lifting of preparing the routine work. The human retains absolute authority over what lands in reality.
That architecture builds immense trust. It doesn't pretend to be omniscient. Another amazing example of this human-AI interaction boundary is GenAI and their Vision UI system. This is completely different from healthcare. This is about conversational orchestration, operating over incredibly clunky legacy enterprise systems.
GenHappy tackles the very real, very frustrating reality that most massive enterprises are not running their operations on brand new, sleek, API-first software. They are running on complex, visually cluttered legacy interfaces built in the 90s or early 2000s.
Oh yeah, those gray screens.
GenHappy acts as a modern conversational layer that translates a user's natural language request into physical system actions using the Model Context Protocol.
So if a logistics manager types, reroute the shipment for ACME core to the Chicago warehouse, the GenHappy agent actually navigates the legacy logistics software, clicks the right buttons, and executes the change.
It drives the software like a human would.
But how does it handle the handoff when things are inevitably ambiguous? What if ACME core has 3 different active shipments?
It uses a technique called incremental parameter resolution. It flat out refuses to guess what the user's underlying intent is. If the user asks to replace a vehicle in the fleet management system and there are multiple vehicles that fit the vague description, GenHappy stops its execution pipeline. It escalates back to the human and explicitly asks for disambiguation.
And the way it asks is the coolest part of the entire tech stack, the Vision UI mode.
It is incredibly intuitive. When it needs human help, instead of just sending a text message in a chat box, Vision UI physically overlays neon visual cues directly onto the user's legacy enterprise screen.
I'm picturing a massive, gray, Excel-like fleet management dashboard from 1998, and suddenly the AI draws a glowing yellow box around a specific drop-down menu and says, "Did you mean this truck or this truck?"
Exactly. It visually guides the human's attention directly to the point of friction in the legacy interface and assists with the selection, but it preserves total manual control for the user. It bridges the massive gap between a modern conversational intent and a legacy graphical interface, enforcing explicit physical human confirmation before it executes any high-stakes, irreversible task.
It's the perfect synthesis of everything we've talked about. Agent maturity is ultimately defined not just by what it can do autonomously at light speed, but by what happens at the boundary of its capabilities.
That boundary is everything.
It's about how gracefully the system can stop, compile a structured SBR context packet, highlight the exact problem, and say to the human, "I have hit my operational limit.
Yeah.
I need your domain expertise, and here's exactly what I need you to look at."
That boundary management is the ultimate synthesis of our deep dive today. True enterprise scale in the AI era is not about throwing billions of dollars at securing the absolute biggest, most power-hungry foundational model in the world.
Right.
It is about building robust, verified, shared memory pools. It's about designing specialized orchestration patterns, pipelines, hierarchies, ensembles, and swarms that fit the specific task. And most importantly, it is about architecting elegant, structured escalation contracts that keep human intelligence firmly in control of the final outcome.
We have covered a truly massive amount of ground today. We started with the concept of the Michelin star kitchen of orchestrating agents, diving into how they divide labor to save compute costs.
A lot of moving parts.
We explored the dangers of the context dump fallacy and how the Delum architecture uses mathematical verification to solve the shared memory crisis. We looked at swarms, acting as lightning-fast SDRs, and adversarial scientists navigating the CDC's datasets. And finally, we broke down the critical escalation contracts needed to prevent consent fatigue and keep humans safely in the loop.
I want to leave everyone with a final, provocative thought, heavily inspired by the writings of Peter Berkholm in our source materials. He argues that scientific and enterprise acceleration is no longer a question of who has the fastest, most capable base models. We have effectively reached the point of commoditized intelligence.
It's no longer just an arms race for raw compute and benchmark scores.
No, the real differentiation lies elsewhere. The future belongs to those who learn how to build research environments that think. You have to ask yourself a hard question about your own infrastructure. If your company's digital memory degrades and hallucinates every single time an AI agent passes a task to another agent, or worse, every time it escalates a task to a human, are you actually building compounding organizational intelligence? Or are you just funding a very fast, incredibly expensive, highly sophisticated game of telephone?
That is exactly the question you need to ask yourself when looking at your own tech stack and your own workflows. If the X-ray machine is broken, you can't just buy a faster, more powerful X-ray machine. You need to step back and design a fundamentally better diagnostic process. And that brings us to the end of our exploration today. Thank you so much for joining us. If you found this breakdown of multi-agent systems and escalation contracts valuable, please drop a like on this deep dive. We'd also love it if you leave a comment below sharing your thoughts. Specifically, how could your own team utilize an orchestrated AI swarm? What operational bottlenecks could you solve with a hierarchical manager or a verified memory pool? Don't forget to subscribe for future deep dives as we continue to decode the bleeding edge of data, automation, and artificial intelligence. Keep diving deep, keep building smart, and we'll see you in the next one.